Hello everyone. In this video, we'll be discussing a bit about pulleys. Now, these pulleys that we have, they are also, the system is an Atwood's machine. Well, that simply has the pulley that you use, that you might have come across in gymnasiums or even in while using it to take water out of a well, right? So this is more or less a pulley which is tied to or which is hung by a rigid support. Here is the rigid support, and this rigid support again has a bar attached to it, which has an axle-like system. About this axle, the pulley is free to rotate, and it has strings or even ropes attached to it, and then you have the masses on either side. Well, on one of the sides, instead of having a mass, if you are to draw water from the well, on one side you can have the bucket or the pail, and the other side you can just put use the force in the downward direction. When you drag this one in the downward direction, obviously this thing goes up, and that helps to that eases the you know uh, the process of taking out the water from the well, because as we are applying force, we are applying a pulling force in the downward direction, which is aiding to the effort, as it is reducing or it is negating the weight of the object that is being pulled up. We'll see, if we have two masses on either side, let this be M1 and this be M2, then how does the process of how does the system work altogether. Now the string, in this case we are having a very simplistic approach, where the pulley is almost considered to be massless. We are not considering or concerned about the mass. Is a very simplistic model of what we are to continue with later in some other video, maybe, because that's this thing that we are studying right now is in the school and the high school and the higher secondary level. Gradually we'll be moving over to the higher levels of pulley system, but that is for the other videos to come. Now this mass over here, let us suppose M1 here is greater than M2, so obviously you can expect the system to be accelerating downward along the mass M1, and at the same rate this M2 will be moving up, but all of that will be against the gravitational pull of the earth. Now the pulley is massless, the string here is inextensible, because because it is inextensible, the tensions that are built up along the string, they will just be cancelling out each other, so they will be directed towards the pulley, finally cancelling out each other. Had the tensions been different, that might have, now this is a steady system where the pulley is fixed, so obviously the with the inextensibility available, the tensions will definitely cancel out each other. Had this system been in an accelerated frame, which we will be considering later, then things would have been different. Most of the cases, when you have these inextensible strings, the tensions must be the same, so that obviously the tensions, one of the tensions being greater, the string extends or gradually breaks, so that really doesn't count to the inextensibility. So the pulley here is massless, the string here is inextensible, and the system is smooth or frictionless. So a lot of things to take into account uh, than the general case. This is the ideal case, the basic level of understanding the system. Now, with the weights of each of these masses acting downward because of the gravitational pull, what we have in this case is that with the mass m1 to be accelerating in the downward direction, we have the free body case for m1 as the tension that acts in the upward direction and the gravitational force that acts in the downward direction, while the acceleration acts in the downward direction. So from this we can have that m1g, that is the force in the downward direction, is greater, and that's why that minus the tension along the string simply is m1 times of a. This is a basic equation of motion that can be involved with this body. And what about the mass m2? Now m2 is obviously accelerating in the upward direction, and the tension acts in the upward direction, while the weight of the object acts in the downward direction. But because the acceleration here is up, so we can say that the tension is greater, which is resulting in the net acceleration in the upward direction. Now with these two equations available, we can just add them up, and adding them we have the t's to be cancelling out each other, and with the t's cancelling out we simply have m1 minus of m2. Obviously m1 was greater, so m1 minus of m2, this is a positive term. We have the acceleration due to gravity g, and on the right hand side the masses get added with the common acceleration in terms of magnitude of the acceleration. The acceleration is common in both the cases in terms of magnitude, so we have the acceleration simply to be equal to m1 minus m2 divided by m1 plus m2 whole multiplied with the acceleration due to gravity. Now in case we cut down the string, now the masses become free and they fall with an acceleration which is equal to that of the gravitational acceleration. Now that is quite the same, because the masses are no more connected, they are independent masses, so they will be applied with the gravitational force only. And so as being connected, they are not free and they are in a constrained form of motion. Obviously their acceleration will be less than the acceleration due to gravity, and that is why you have the numerator to be having a minus term, which is making it less than the denominator, which is obviously greater. Now if the mass m1 had that been greater, much greater than m2, very heavy, then that uh, when we add m1 with m2, or we subtract m2 from m1, that wouldn't have really made a difference. In that case m2 would have been neglected and a would have been equal to g, which means that would have resulted in a free fall, almost a free fall, considering the case that there is no friction and massless pulley is considered as well. Now this is one of the form of the Atwood's machine, and another approach that we can have is this system to be having a compounded form. That is, if we have the pulley, one of the pulley is over here, it is fixed as in the above case, and on the other side we have a mass over here, and on the other side what we have is we have another pulley which is a movable one. Movable in the sense that it can go up or down as per the forces involved. and that again has an inextensible string connected to it, which carries two masses. Now, what is the condition for acceleration, and what are the equations that we can involve with it? Well, let's just start off with the masses. Over here we have an M1, we have an M2, and let this one be M3. Three different masses, and with that, again, the condition almost is the same. That is, the pulleys are massless, the strings are inextensible, and we are obviously taking the smoothness into account in this case as well. Now, with that being the case over here, what about the acceleration of the system? Now, the acceleration over here is the acceleration that M3 experiences. Let that be simply A. And the acceleration of the masses M1 and M2, because the masses will obviously follow the rule as in the above case, but there is a special condition to it, that there's a this whole system, this system, let me uh, take that in the dotted box. This system that we see, that is also a collection of uh, masses altogether, where the pulley is considered to be massless. That system altogether is accelerating, and in an accelerated system we can afford to take the accelerations of the different of the masses given as a1 for the mass m1 and a2 for the mass m2. Why? Because the acceleration here will be in terms of the relative motion, or the relative acceleration between the first, let this be the first pulley and this be the second pulley. So the relative acceleration between the strings of the first pulley and the second pulley. So that is why the A1 and A2 can differ in this case. Now we have a common ground for this entire system, and we take a few adjustments or measurements in a different way, so as to first of all bring the condition of relation between the accelerations that we have at hand. Let this fixed pulley from the ground be at a length L, which is capital L in this case. The distance of this arm of the pulley over here is, let us say, small l, that is from pulley 1 to pulley 2. And let me write that in a different ink for you, for your better understanding. This is small l. Let this distance be x3. This is x2, and this one is x1. Right, I write it on the right hand side for proper viewing. This is x1. Now the strings are obviously inextensible, so their lengths are never going to change. Now, what is the length of the string that is over the pulley 1? The length of that string can be written as L minus x3, which is the length of the string from the pulley 1 over to the mass m3, that plus the length L that is over there on the right hand side. Okay, and that length obviously is constant. Why? Because that's an inextensible string, remember. What about the second, the rope or the string that is over the pulley 2? Now that length that we see over there is simply Well, we have it as L minus L, that is the distance of the pulley 2 from the top. So we have reduced that. What about the left string, that is for the mass M2 from the pulley? That is equal to this length L minus L minus x2, and then we have the other side of the string, that is L minus L, that is the length of the pulley from the bottom of the from the ground level, and that minus x1, and this gives the length of the string uh, of the pulley 2 over the pulley 2, and that is also a constant as well. uh, you can have a more simplified approach if you think of it, but as of now, that is, these are the lengths, or these are the things which are striking to me as per my notations. Now this can be just simplified as 2 times of L minus L, that is taken common, minus of x1 plus x2, which is a constant, of course. Inextensibility comes into account. The These two equations that we see over here, this one and this one, they have constant values. Now with those constant values we can come up with something. Let's see what we come up with. So let's just consider these two equations once again. So uh, we can multiply a 2 over here. The only variables in this, L is a constant, of course, because L is the length, the fixed length of the pulley 1 from the ground level, and we can, however, get rid of the this L over here just by multiplying it with this equation with the 2, and with that multiplication we add these two equations. uh, Adding them, what we get is 4 times of the L, that is the constant length, minus 2 times of x3 minus 2 times of actually it's not 2, it's just the single bit, that is x1 plus x2, and the small l's have cancelled out, and what remains on the right hand side, because we had constant values on the right hand side, constant multiplied with another constant over here, that is 2, and then added to another constant, that will result in a constant every time. Now with this relation available to us, let me just take it to the next page. We'll be returning back to this page. So with this equation available, I'll be writing it once again. We had 4L minus 2 times of x3 minus of x1 plus x2 in brackets, and we had a constant value over here on the right hand side. Just taking the derivative of this entire thing with respect to time, the variation with respect to time, what we have is, we have 2 times of v3, which is the speed that is acquired, or the velocity that is acquired by the third mass, and over here we have v1 and v2, that is the velocities of the other masses. The derivative of a constant quantity goes to 0, so with L being constant and the right hand side being a constant as well, that results in 0. So the first term is 0 and the term on the right hand side goes to 0. Taking the derivative once again, we have a minus, so we take the derivative once again just to obtain the relation with the acceleration. So this is a3, that is the acceleration of the third mass, and this is simply A1 plus A2, that equates to 0, and so we have A3 to be equal to A1 plus A2 divided by 2, and obviously direction wise we can say that it's exactly in the opposite sense of the accelerations that are in the second pulley. So with this relation available to us, we can just move ahead with a numerical that is associated with this kind of system. Now we have the same case where we have the fixed pulley at the top, and the masses that we have over here are simply uh, the 1 kg mass on this side. Then for the other pulley that we have, the masses are 2 kgs and this is 3 kgs. Now we wish to obtain the acceleration of the individual masses. In order to do so, we'll be using this relation that we have at hand. But before that, we will add a few parameters to this. Now the parameters that we can add over here are the tensions along the string. So let these be the tensions. That is, we have the T to be the tension along this string, while we take the tension along this string as T primed or T dash. With these tensions available, what we see over here from this uh, case, now the tension T dash has to be equal to the sum of the two tensions that are developed along the string L2 or the pulley 2 for an equilibrium system. Now for that we have T dash to be equal to 2 times the tension that is developed along the string L2 in the pulley 2, and so we give the equation of motion, and this mass 1 over there, 1 kg, that uh, obviously we will be considering the accelerations, and the accelerations on the whole will be considered along a specific direction. We take the entire system to be accelerating downward. This is a separate form of approach rather than the one that we discussed earlier in the video. So we consider all the masses to be the net acceleration to be acting in the downward direction. So we have the mass 1 kg to be multiplied with the acceleration due to gravity minus, this is not 1 gram but this is 1 times of gg being the acceleration due to gravity, and T dash is the tension along that string we are considering for this mass over here. So that is equal to 1 times of A. Let A be the acceleration of this given mass. Now from this relation that we have, instead of A3 we have A over here instead of A3. So we just take it that way. We can however use the A1, A2s that are there for the masses 2 and we say suppose this is A1 and this is A2, and then we move over to A over here. So A1, A2 and then A on the extreme left. So for A, what we have is that to be equal to minus of, we take the minus out, we can skip the 1 uh, for easier calculations. So we have A1 plus A2 divided by 2, and this obviously gives me 2 times of g, the 2 gets cross multiplied, minus, well, instead of T dash, what we can have is we can use this relation. So instead of t dash, what we can use is the 2 gets multiplied on the left hand side, so 2 times of t dash, 2 times of t dash. Instead of t dash we use 2t, and we have minus of a1 plus a2 over here. So that ends up with 2g minus 4t, and that is equal to, this minus is common over here, a1 plus a2. Well, that is one of the set of equations that we can get over here for that that left hand side, that is the 1 kg mass. What about the 2 and the 3 kg mass? Well, for the 2 kg mass, we have as the acceleration is again considered along the same line, we take it see, in case we take the acceleration, one of the accelerations to be acting upward and the other one in the downward direction, eventually we will have a negative sign associated with it, which will finally give us the result that we want. So it's not mandatory that we take the acceleration along the upward direction for one side and the downward direction for the other side. So the equations, they take care of themselves in the process. So here for the second mass, we have 2 times of the acceleration due to gravity, that is the weight of the object, minus the tension that is along that line, that is t. Free body you can consider that we had done previously, and we are considering the acceleration again in the downward direction. So 2 times of a2, 2 being the mass, times of acceleration. What about the third object or the third mass? So 3 kg times of the acceleration due to gravity minus t equates to 3a1. Now with this available, we can just add them up. From these two, adding these two, we have 5g and minus 2t equals to 2a1, no, 3a1 plus 2a2. Seems fine. And well, let me just take the minus, the negative form as well. It will be handy for calculation because we have 3 variables over here, and we just want to reduce it to 2 variables for our convenience. And for that we need to get rid of the t, that is the tension along the string. So for that, what we do over here is that we just take the negative of one of the equations. Let the first equation be taken as negative, so we take minus 2g plus t equals to minus 2a2, and we add it up with 3g plus minus t, and that is equal to 3a1. So the second equation remains as such. The first equation, we have taken the negative of it and we add these two, so we get rid of the t's, and what we have is 3g minus 2g is simply equal to g, and that is equal to 3a1 minus 2a2. Well, that is another equation. From this equation that we have obtained over here, we can consider these two equations now, and from these two equations, I write it over on this side. What we can do is we can again get rid of the t, and for that what we need to do is we just need to multiply this equation that is over there, that is the second equation, that is the second one over here. We can just multiply it with a minus 2. Minus 2, what does that do over? For that we get minus 10g plus 4t equals to minus 6a1, and this is a minus 4a2. Well, that now can be added to this equation over here, and when those two are added, I'm doing it directly over here without rewriting it, we have minus 8g. The t's cancel out, and for the a1 and a2 terms, what we have is, it is a minus 6a1 minus a1 gives me minus 7 A1 seems fine, minus 4A2, and minus A2 again gives me minus 5A2. The minuses can be kept common over here, and we can just get rid of them right away. Now we are reduced to two variables and we can obtain the accelerations individually. And if you calculate that, well, let me just calculate that for you in case you're having problems with it. Well, for getting first of all, we need to find A1, and in order to do that, we just multiply this with 5 and this one entirely with a 2. What that does is that we have 10A2 and minus 10A2 on both the equations, and well, adding them they can get cancelled out, and in the process what we are left with is that this equation has 16g, and that is equal to 16g, and what about this one? This is 5g, so 16g plus 5g for this, because 5 was multiplied on that side. And on the right hand side we have the a1s, that is the 14a1 for this from this equation, and from this equation we have 15a1, so that is 15a1, so that adds up to 29a1, and this is simply 21g. So what we have is the value of a1 to be equal to 21 by 29 g. This is the value of the acceleration, and for which mass? Is obviously for the 3 kg mass. Now from that we can easily calculate the value of A2. Let me just put it in this equation if you wish to. So this is G, and that is equal to 3 times of A1. A1 has the value now 21 divided by 29 times of G minus 2A2. So the 2A2 can be taken over to the other side, so we have 2A2 equals to 3 times of 21 is 63 divided by 29, 63g, minus the g that has come to the right hand side, that multiplied with 29 gives me 29g divided by 29 as a whole, right? But 63 minus 29 is simply equal to, if I'm right, it is 34. So that's 34 divided by 29 times of g, and here we had a 2 factor which gets cancelled out, so A2 is simply 17 by 29. Let me rewrite it for you once again, 17 by 29 g. That is the value of acceleration for the second mass over here. And from that we can have the value of A. Remember, A was simply equal to A1 plus A2, but in the opposite sense, of course. We are concerned about the magnitude in this case. So A is simply equal to A1 plus A2 by 2, that is 17 plus where is the A1? If I'm getting, yeah, it's right above it. So A1 is over here, that is 21 by 29, and this is 17 by 29. That when added gives me 38 by 29. 38 by 29 divided by 2, so that 2 is divided and that times of g, so this is simply in 19. So this is 19 by 29 g. This is the acceleration, but as you know, this is in the negative direction. As far as direction is concerned, it will go up as per the equation that we have over there, which is, see, we need not consider the acceleration in some other direction right from the beginning. From the beginning over here we have considered all the accelerations in the downward sense. So from that, because you see, in case you may think that A2, the mass 2 kg, will be dragged upwards because the 3 kg is heavier and it will go down, so mass 2 kg may go up. But if you consider the system as a whole, that system is going down entirely because the masses 2 kg and 3 kg on the second pulley, they will be dragging the entire system downwards. So as a whole, A2 will be directed in the downward direction as well, which is quite easy to determine from these positive values that we have obtained for these two accelerations, A1 and A2. While we have obtained, in case of magnitude, this is positive, but actually it is a negative, means it is going in the upward, it is negative, so that means it is headed upward or opposite to the direction of the accelerations A1 and A2. So this is one of those typical problems that we can relate to such a system. You can have more such systems. Remember, the pulley can be attached inside an elevator which is accelerating in the upward or in the downward direction, and then you have the net accelerations. Remember, the accelerations and the velocity equations are always the same for most of the systems that we have here. Even in the second line, if you observe the velocities, the relation between the velocities, we have v3 to be simply equal to minus times of v1 plus v2 whole divided by 2. So that is also a relation that you can use, but equations of motion, usually these forces, they usually deal with the accelerations, so velocities are not that much necessary. We would rather stick to this important form of the equation. There are more of these uh, such type of questions. You can mail that to me if you want to, and in case you have an easier method for this, the relative acceleration method is easier as well. But on a basic level, this will help you understand this entire thing as a whole. So I took this approach. For more problems, we'll be discussing that for the videos later on. Till then, thank you for watching.